Welcome to the lesson on mass transfer in fluids. This is taken up as part of mass transfer, which is under the NPTEL MOOC on transport phenomena in materials. The topics that we are going to take up in this lesson are as follows: stagnant layer approach, mass transfer coefficient, film theory, Higgs's penetration theory, surface renewal theory, and Sherwood number. So the stagnant layer approach is as follows. In a domain, we have two species that are diffusing in opposite directions. In such a situation, will the Fick's law be valid? And how would the diffusion profile look like? And how do we evaluate the flux of the species? These will be taken up under this section. So the domain is as follows. You have basically a crucible, and at the bottom of the crucible there is a reaction that is leading to generation of species A, and the species A is then going up the crucible, and the crucible is actually being flushed with gas, which is basically the other species B. So as the species A is moving up, to replace its positions, the species B is coming down, and because of the crucible being flushed on the surface with the species B, then what happens is that the composition of A at the top of the crucible is almost zero. The domain that we choose for this problem is indicated with these dotted lines. The axis variable x is indicated going from the bottom of the crucible towards the top. So we designate that the bottom of the crucible is where x is equal to 0, and the top of the crucible is where x is equal to L. So in our domain, the boundary conditions are as follows. At the bottom, Ca is equal to Ca naught, and at the top, Ca is equal to Cal, which means that the species whose concentration we are interested in is A, and B is what we would actually have as a stagnant layer, hence the name. So because the two species are present, the total concentration is being assumed as constant. So that's the first assumption that we are making in this particular problem. And this concentration then can be expressed as Ca plus Cb is equal to C naught, and we want to have C naught as constant, which means that when we differentiate with respect to the variable along the x-axis, that is the distance variable, then we notice that dou Ca by dou x plus dou Cb by dou x is equal to dou C naught by dou x, which is 0, which is giving us the relationship that we will be using a little while from now, that is dou Ca by dou x is equal to minus dou Cb by dou x. Now the total flux of the species can be expressed, and we need the advection velocity. We have not been using it in the previous lessons, but here we need, because there are two species and they are moving in the opposite directions, so there definitely must be the motion of the center of gravity for this species, and that we denote by U. So the total flux of species A is written with the summation of the diffusive flux and the term coming from the motion of the center of the mass. So notice that there is no asterisk on top of J, which means that what is written here is a total flux. The diffusive flux is what is the first term on the right hand side. Similarly, the total flux of the species B can be also written using the concentrations of the species B. And we make an important assumption here, which comes under the model being called as stagnant layer. That is, the species B is moving in such a way that the total flux is 0. So one may ask, if a species doesn't move, then the total flux is 0. But actually what we want to say is the total flux Jb is 0, which means that the gradient of B is in such a way that it counters the advective velocity here. Okay, so these two terms are cancelling, therefore the total flux actually will be 0. So this is an important assumption that we are doing. So by making this assumption, what we are actually getting is an expression for the advective velocity U in terms of the gradient of the concentration of species B. Now this expression is important for us, and we are going to note it down for immediate use. Now the total flux of A can be written in a way that we can actually express it only in terms of the concentrations of A. So we just now got the expression for the advective velocity u, and in that we have the dou Cb by dou x, which we want to replace with dou Ca by dou x, that we have the expression from there. We also have in the denominator Cb, which we want to replace with Ca because we have the relationship here. We can do that. And this expression of u written in terms of only the variables for A can be plugged into the total flux of A. And then we can obtain this expression as follows, where the first term is kept as it is, so the second term is obtained by substitution. And when we gather the terms, we realize that it can be simplified as follows, where the flux is equal to minus d into dou Ca by dou x into a term C0 by C0 minus Ca, which already indicates that it is not directly the Fick's law, but there is some additional component that is coming as a multiplicative factor. Now the other assumption, the third one what we are going to do is to say that the species A is actually moving in a steady state. So when there is a steady state, that means that the total flux, the gradient will be 0. This we can refer to the derivation of the governing equation and see that there is a step here which indicates this particular relationship. In the absence of a generation term, this actually comes out quite neatly. And in 1D, we can write the expression as dou Ja by dou x is equal to 0, which is quite simply just one component of the above summation. And for Ja, we substitute the expression that we have derived just now. And when we do that substitution, then we see that we get an equation which tells us how the variation of the concentration of A will be governed. So here is the governing equation for the variation that we have obtained for steady state motion of the species A, and for the total flux of B being 0. Okay, and A and B are actually moving in the opposite directions. So now we can actually formulate the problem properly as follows. We say that the equation that has to be solved is like this, and it has to be solved subject to boundary conditions, which are namely Ca is equal to Cal at x is equal to L, and Ca is equal to Ca naught at x is equal to 0, which we can do that by writing down the equation and integrate once, and we see that we can basically have the integration constant as say P1, and then we can integrate once more. For that, what we do is take these terms to the other side and then integrate them going from 0 to x for the x variable, and appropriately Ca naught to Ca for the Ca variable. And once we do this integration, we get on the left hand side the logarithm and on the right hand side only the x. So we can get the answer as follows. So the minus comes because there is a minus here, so that has to actually come. Now once we have this, then we can use the second boundary condition to determine what would be the expression for evaluating the P1. So when we substitute x is equal to L, then Ca should be Cal. Once we do that, we can eliminate P1. Okay, so we eliminate P1 from this expression and then write the solution in this elegant form. Now as you can see that it is actually relating the logarithm of the concentration ratios with x and not directly the concentrations with x, which means that the solution is different from what we have obtained for a planar case of the steady state diffusion equation starting from Fick's law. And in case the crucible is containing the species not in a liquid but in a gaseous form, then the partial pressures can also be used as a measure for the concentrations, because from the ideal gas assumption we can actually write the concentration of species A as Pa by RT, and we can then see that RT will get cancelled everywhere because concentrations are appearing as ratios. So we can also have the expression in terms of the logarithm of the ratios of partial pressures related to the distance, which means that the way the pressure is going to vary, partial pressure of A is going to vary from bottom of the crucible to the top, is actually logarithmic when we look at this expression. Now, one of the ways of applying this is as follows. We have got this expression for flux which we have derived earlier, and into that we substitute the expression or solution for Ca, which means that basically we treat this denominator anyway is a constant that doesn't appear, and this entire thing is a constant. So from here we want to only differentiate this, and so dou Ca by dou x can be obtained from this solution. We substitute that and obtain the solution for the flux. So you can now see that the flux expression is available. Now, why is this useful? This is useful because when we know the cross-sectional area from the crucible, which is actually undergoing this particular process A. So when the cross-sectional area is available, then when we multiply with the flux, we get basically the mass loss. Okay, and mass loss measurements can be done in an equipment such as the thermogravimetric analysis. And once we have the mass loss being calculated, that means we have got the Ja, and if we have a way to measure the compositions, all of these terms are known. The geometry of the crucible will give you L, and that means that we now have a way to measure D. Okay, which means that the diffusivity can then be determined. Now these measurements are very valuable because among all the transport phenomena, it's the mass loss experiments that are most accurate. Why we say is this? Because in a very not so expensive equipment, we can still get a microgram accuracy for mass loss, and when we look at the such accuracies for velocities or temperatures, we definitely do not have that kind of an accuracy. So which means that evaluating the diffusivities using this kind of a setup for a gaseous species is quite accurate. Now we have this expression that we have derived, and we can compare it with the solution from the Fick's law, and we notice that whenever we have a mixture of two species that are having the counter diffusion, then Fick's law is not sufficient because we don't have a way to explain how the logarithm is coming directly only from the rectangular case solution for Fick's law. However, when the solution of the two species A and B is very dilute, and assuming that Ca0 is 0 at the one end of the crucible and Cal is small, let us look at the way this expression looks like. Then you can actually see that it would actually give you a solution that actually almost looks like the Fick's law solution, which means that you can ignore the second species and the advection term and use Fick's law only when the concentrations are dilute, which means that for concentrated solutions which have significantly high value of the volume fraction of the two species, then you should actually use expressions like this rather than just the Fick's law. We come to the mass transfer coefficient, the section where we want to introduce this concept analogous to the heat transfer coefficient in the Newton's law of cooling. So we look at the concept map that we have developed earlier for different boundary conditions, and I have put a star here to indicate that we are actually looking at one of the ways of specifying the boundary conditions where the flux is being specified in terms of mass transfer coefficient. The reason why we actually introduce this concept is because sometimes the gradients are very difficult to estimate, and particularly in fluids where there is an advection which is changing with time, etc. Then we are forced to write the mass flux using simply a constant times the difference of the compositions that are relevant. And the first value would be the concentration at the interface between the solid and the fluid, and the second is the reference concentration far away from the interface of the solid and fluid. So difference of these two compositions is being used as the measure of how the flux is going to be there, and the coefficient is nothing but the mass transfer coefficient. So we are introducing this very similar to the heat transfer coefficient, and like heat transfer coefficient definition, the mass transfer coefficient is also taken always as a positive quantity, which means that irrespective of the direction you are actually using for the convention of mass flux, you should actually take the magnitude of it divide with the absolute difference of the concentrations as relevant, and write the mass transfer coefficient as a positive quantity. And as you can see from here, the units of mass transfer coefficient are same as that of velocity, meters per second. Now we look at some of the examples to illustrate how this mass transfer coefficient can be evaluated. So one case study is mass transfer between a sphere and the surrounding liquid. And the way we evaluate mass transfer coefficient is using the diffusion profile, which means that in the concept map for boundary conditions, we are using the concentration profiles to arrive at the mass transfer coefficient, and therefore the flux, and therefore the boundary condition. So consider the situation to be diffusion of a species from a sphere into the surrounding fluid. The sphere is having a radius r, which means that our domain where the diffusion is taking place is from radius going from capital R to infinity, and the solution is then being taken up with the following assumptions. So we assume that there is a steady state for this diffusion, and it is unidirectional, that is only radially outward diffusion of the species, and the fluid around, the fluid is all around, and the species is going in this direction away from the sphere. And we assume that the fluid is quiescent, which means that there is no velocity in the fluid, and therefore we can actually take only the diffusion term alone for the governing equation, and also only one dimensional and without any reaction also, and steady state. So which means that we have only one term from the governing equation that will be playing a role, and it just comes as one term which is equal to 0. So which we have to solve against the boundary conditions, namely at the surface of the sphere the concentration of the species is C0, and far away from the sphere the concentration is C infinity. Now the solution is coming out quite straightforward as Ca is equal to C infinity minus capital R by small r, C infinity minus C naught, which you can already see that at R is equal to capital R, which will give you C naught, and at R is equal to infinity, it will give you C infinity. And as also explained earlier, the concentration is going hyperbolic, that is with respect to 1 by R. That's how the variation is happening. Now when we evaluate the flux at the surface of the sphere, we basically take this particular solution that we have obtained and substitute into the expression for evaluating the gradient of composition, and use that to get the flux at the surface of the sphere, and we evaluate that quantity at R is equal to capital R. And we know that this flux has to be then defined as the mass transfer coefficient Ka times the difference of the two relevant compositions, which means that we are actually using the definition of Ka to evaluate. So whatever we get from here, we substitute there and evaluate, and when we perform these simple manipulations, we get a very simple expression for the mass transfer coefficient, which is nothing but the diffusivity divided by the radius. And this we have obtained by looking at the analytical solutions. So we can actually evaluate the mass transfer coefficient using the composition profiles also. Now for other situations you will have little more involved problem descriptions, and a very early solution was proposed by Lewis and Whitman in 1924, which goes by the name film theory. So this is where at an interface between the gas and a liquid, how does the composition vary, and how does it actually help us in determining the mass transfer coefficient. So the assumption in this model is that the interface between the gas and the liquid, where the solute transfer is taking place, is actually happening over a thin region, a film like region, which the thickness of that is given as delta, and the flux is actually taking place across this film thickness. And we also assume that this being very thin film, the concentration profile is linear between them, and the two relevant concentrations are CSA and C infinity A. So we can write the definition of the mass transfer coefficient as we have given earlier, and because the gradient here is linear, by using the Fick's law, you can actually already write the flux as minus d into the gradient, which is nothing but the difference of the concentrations divided by delta. So by comparing these two expressions, then we can determine what is Ka, which comes out basically saying that it is basically d by delta. So which you can see earlier, and now that a relevant length scale is coming in the denominator and giving the mass transfer coefficient. This is a very simplified assumption, and that goes by the name that it is a film model. Unfortunately, we do not have a very easy way of measuring what is this delta, and therefore the uncertainty in delta will transfer onto the uncertainties in the mass transfer coefficient as well. So this has been improved by Higbee in the paper in 1935, where the estimation of mass transfer coefficient was done using the diffusion profile. And in the concept map that we have discussed, basically we are saying that we are here where the Higbee's model is being used for mass transfer coefficient. So the description is as follows. When a packet of one fluid is exposed to another fluid, so that is liquid and gas for example, then for a small duration of time, the packet of liquid faces unsteady state diffusion, and which means that the solute is going to be penetrating into the liquid packet during that contact time. And we already know that for unsteady state diffusion we have composition profiles already evaluated using error function. So that is the intention of talking about this small amount of contact time. And during this time the liquid is actually internally stagnant, which means that during the time this particular composition evolution is actually taking place, it is stagnant internally, but then after some time the liquid packet will move away and gets well mixed with the rest of the bulk liquid. So this is the model that has been proposed by Higbee, and using this model then we can propose that there is a composition profile that we are talking about, and in the thin layer you can actually see that the composition profile can be assumed to be given by the error function solution, because the shape looks somewhat like error function. We choose the distance variable such that it goes into the liquid packet, and then we can write the solution as follows: Ca is equal to Ca naught f of x by 2 root dt. So where x is equal to 0, you get Ca is 0 here, and when x is equal to infinity you get Ca naught here, which means that this particular domain is quite big, so that semi-infinite domain can be reasonably approximated. And so we can actually now say that the flux of A arriving at the gas liquid interface is the same as what is leaving into the fluid medium, and vice versa, which means that the flux that is evaluated by looking at the gradient of the composition profile can also be equal to the flux that is evaluated using the mass transfer coefficient. Okay, and this is what we write. So first thing we write flux of A arriving at the interface using the composition profile, and x is equal to 0 is the interface, so this part is because it is the interface, and this is known from the error function solution. Okay, so we then substitute that and substitute this into there, and then we already know how to differentiate 2 by root pi e raised to the power of minus eta square. Eta is x by 2 root dt, and we will not forget that the differentiation with respect to dx, so which means that dou eta by dou x has to come, and that's the reason why this additional factor is going to be there. And this we evaluate at x is equal to 0, which means that this entire thing is going to be unity, and 2's will get cancelled, and the d here is going to cancel with the root of d, leaving one root of d in the numerator. Pi and t are here in the denominator, and Ca naught is from here. So we get basically the flux as Ca naught into root of d by pi t. Now when we want to express the same flux as leaving the interface using the mass transfer coefficient, we would write the same way as Ja is equal to k into Ca naught, and at the interface the composition is 0. Okay, so which means that when we compare these two expressions, then we notice that Ka is nothing but root of d by pi t. Now this is actually the instantaneous at any instant. So this is actually instantaneous mass transfer coefficient and we can actually ask what would be the averaged mass transfer coefficient. So when we want to average, basically what we take is whatever we want to average, we actually take it and integrate with respect to time and divide by the total time over which we have to average. So the denominator is actually t itself, so we substitute the expression for k, and that's what we have done here. And then when we evaluate, we get 2 times root of d by pi t. So this expression is then giving you an average. So sometimes people actually put a bar on top to indicate that is an average mass transfer coefficient. So this is a very useful expression. So this t is giving you the time of the interaction between the fluid and the gas, and d is the diffusivity of the species in the fluid, and it will tell you how the species is actually getting transferred. So for degassing and such problems, we can apply these kind of solutions and evaluate how the solute transfer is taking place. Now the application of this kind of a relationship is also there even in situations where it is not an intermittent but actually for a steady state flow also. So here what we are seeing is a continuous casting setup where we see that liquid metal is actually getting poured. So there are several locations where the liquid metal is getting poured. So here is one place it's getting poured, here is one more place where it is getting poured. So whenever that is happening and the liquid is flowing at a constant velocity, then you could actually see that the distance over which it has to flow divided by the constant velocity with which it is flowing is giving you a scale of time over which this particular interaction is happening between the liquid that is flowing and the gas that is surrounding. So at that juncture there will be a solute transfer and perhaps oxygen pickup, for example, and we may want to evaluate what would be the mass transfer coefficient that is relevant. So instead of t, we can actually use z by u and substitute, so that instantaneous mass transfer coefficient is then given by root of du by pi z in situations where there is a flow of metal at steady velocity u and over a distance z. Now we come to the section on surface renewal theory, which is actually an improvement of the previous two theories for the mass transfer coefficient. This is for the diffusion across the gas liquid interface where there is a particular time scale that is involved, and this has been published by Danckwerts in 1951. You can see the chronology how these developments have been taking place. So here is the concept. Usually in metal processing, what happens is that there is some agitation or bubbling or some kind of a regular motion that is introduced in the liquid, and the interface between the gas and liquid is such that it is actually intermittent, and there is only a probability of a piece of or a pocket of liquid that is coming in contact with the gas. In the case of gas bubble that is going through the liquid, then again is the same thing, that as the gas is moving there is a probability that is involved where the liquid is coming in contact with the gas. So in such scenarios, so what we want to say is that there is a particular time scale that is relevant for this particular interaction, so that we call as tau. So if we know the rate at which bubbles are introduced, then this time can be evaluated by the frequency of how the bubbles are actually moving. So 1 by frequency will give you the time scale, and similarly for other ways of agitation or motions between the liquid and the gas. Now the probability of the liquid packet uniformly mixed with the concentration of species A can be given as this expression 1 by tau e raised to the power of minus t by tau. So here actually we are actually bringing the stochastic nature of this process where the solute transfer is happening between the gas and the bulk liquid, and this probability is given in such a way that it is giving us 1 when we integrate it over infinity. That means over a period of time, then definitely this expression is going to give you 1. And the instantaneous mass transfer coefficient we already saw from the penetration theory, we can actually take it as d by pi t. So instead of saying that this is continuously available over the period of time t, we are actually saying that there is a probability that is involved, which means that we are actually improving on the solution that we have got earlier using this time scale tau. So the way we average is as follows. We basically instead of directly averaging the k, we actually put the f in the numerator and average k. So the average value of k, considering the probability of interaction between the liquid and the gas, is considered in this expression. And in the numerator, the probability f is given with the expression that we have just brought in. And the instantaneous mass transfer coefficient is given by root of d by pi t, that is going in there. And in the denominator, the probability when summed up over infinite time is actually 1, so there is nothing in the denominator. So when we evaluate this by substituting, we write the expression as k is equal to integral 0 to infinity 1 by tau root of d by pi t into e raised power of minus t by tau dt. And this, when we evaluate, we get the answer as root of d by tau. So you can now see that it is actually the square root of d and not d itself that is coming as a proportionality for the mass transfer coefficient. So this is where actually the experimental results were being brought in a little closer by introducing these realities, namely the stochastic nature of the interaction between the liquid and the gas. So one need not be afraid about these evaluations. If you have Sage Math, then you can actually inform Sage that the tau is a positive number and ask what would be the integral. It will give you the answer, and for the second integral also you will get the answer. So you can learn about how to do this in a different course, but for now you can take the answers for these integrals as we have given. So we now bring in the concept of Sherwood number. So Sherwood number is being introduced as an analogous concept to Nusselt number, which we got in the heat transfer. So in the heat transfer chapter, we have heat transfer coefficient which was having units, and we wanted to convert it to a non-dimensional quantity, and then we called that non-dimensional quantity as Nusselt number. Similarly, the mass transfer coefficient has the units, which same as velocity, and we want to convert that into a non-dimensional quantity so that we can arrive at correlations when we perform experiments, etc. And such a non-dimensionalization of mass transfer coefficient is called the Sherwood number. And here we are actually putting it in the perspective where we have the concept map for boundary conditions, and boundary conditions are sometimes given in terms of Sherwood number, and which means that we can then get the mass transfer coefficient and then the flux and therefore the boundary condition. The way we non-dimensional is as follows. The mass transfer coefficient has the units of meters per second, the diffusivity has units of meter square per second, and there will be a characteristic length scale over which the diffusion is happening, and that will have units of meters. So naturally the non-dimensional number would then be given as Ka times Lc by d. So this is the definition. Now the correlations for mass transfer coefficients for different flow regimes and geometries are given in terms of Sherwood number. So when we are looking at how would be the mass transfer coefficient be in a given scenario, we should actually be looking at how the Sherwood number correlations are going to be available. Okay, and for that we illustrate by revisiting the problem of mass transfer between a sphere and the surrounding liquid, where we said that the mass transfer coefficient is given as d by r, and the Sherwood number we have defined just now as KLC by d, and let us say the LC is basically 2r, because normally the characteristic dimension for a sphere is the diameter of it, which is 2r. So when we substitute that, then you see that a very elegant expression has come, that is the Sherwood number for steady state one-dimensional solute transfer from a sphere into the surrounding fluid is just 2. And this is very useful because it is easy to remember. And later on, whenever we want to see what would be the effect of diameter change for a sphere when it is losing the solute content into the surrounding fluid, we can see that the Sherwood number correlations will give us how the flux is actually changing. So the mass transfer coefficient, in which way it is relating to the length scale, is available because this entire thing is basically a constant. So which we can say that Ka is proportional to 1 by the radius, which means that smaller spheres would lose the mass much faster, okay, because its state goes as 1 by r. And later on, when we see the Sherwood number correlations for spherical geometry, you would always see them as 2 plus something, okay, and we now know the meaning of this 2 because that is for the steady state unidirectional solute transfer without advection, and whenever the advection is there, then you have the second term that is coming in. Now these correlations we can put in the perspective with respect to the rest of the phenomena. In the case of fluid flow, we saw that friction factors are important for us to determine turbulent flow, and those friction factors are given as functions of Reynolds number. And in the case of heat transfer, you have the Nusselt number which are being given as function of Reynolds number and Prandtl number. And similarly, in the case of mass transfer, we have the Sherwood number correlations that are being given as a function of Reynolds number and Schmidt number. Now, there is a small set of these correlations that have to be distinguished. In the case of forced convection, it is the Reynolds number that would be used for the correlations, and in the case of free convection, it will be the Grashof number which is used for the correlations. And the Schmidt number that we mentioned just now is nothing but a property of the fluid, because it is a ratio of two properties, the kinematic viscosity over the diffusivity. And so the way we solve the problems in mass transfer, whenever the geometry and the problem description is little tedious, is by first identifying the regime of the flow field, so that we know for what range of Reynolds number or Grashof number we are talking about, and for what geometry. So accordingly, then we can pick up the relevant correlation for the Sherwood number. And once we have that, then we know that it is going to contain these properties which will have various quantities. So we have to plug in all those parameters so that we can get the numerical value of the Sherwood number. Once we have the Sherwood number, naturally we have the mass transfer coefficient obtained directly from there, and of course the length scale has to be known irrelevantly, and then we can get the K. Once K is known, then we can actually determine the flux, because it is directly given as Ka times the difference in the compositions that are playing a role for that particular mass transfer. And once the flux is available, then you can use balance equations to determine what would be the drop in the, for example, the hydrogen content of a liquid metal during degassing operation, etc. And once we have the balance equations sorted out, then the final solution for the concentration can be obtained. So as you can see that even for a very complicated problem, by going through this particular sequence of steps and remembering that correlations of these non-dimensional numbers called Sherwood number are available, then we can actually easily go for any regime all the way up to the solution. And it's just that there's a long path that is involved in the meanwhile. The numerical solutions that are done with simulations are generally using this kind of a methodology, because many of these functional forms are available in tabulated form in some of the databases. And for this lesson, I have taken references as follows: the classical textbook by Poirier and Geiger called Transport Phenomena in Materials Processing. This textbook had enormous amount of data that we would actually require for those solutions. The correlations of Sherwood number also are listed. We don't have to discuss much about the correlations themselves. They're all empirical correlations, and we just need to plug in the numbers and get the values, and we can look up the Poirier and Geiger book for those correlations. And of course, we have also looked at the different mass transfer coefficient models, and these are described both in Poirier and Geiger book as well as in David Wilkinson's book. With that, we come to the end of the unit on mass transfer.